I'll talk about sketching as a tool for algorithmic design. Or at least I'm supposed to, well, this is what the schedule says. In the style of the previous two overview talks, and for those who've been here, I know that by now you expect that I'll cancel this title and talk about something else. I have to disappoint you. I'll actually try to talk about this as much as I can. I mean, it's still hard to talk. So I'll try to, I guess, rather than selling kind of concrete problems, I'll try to, sell you here like more of a perspective about algorithm design. Okay, this is what we're trying to go after. And let me tell you kind of like one problem, in particular, kind of I was working a lot on, or am working a lot on, is the following kind of problem on big data sets. Is given a bunch of objects. In this case, this is a bunch of images taken from the classical ImageNet data set, and you want to find the pairs of similar objects here. Okay, and there are kind of two issues. I mean, one is that there are too many objects here, so pairwise comparison of objects gives you quadratic algorithm in the number of objects, but also comparing two objects might be difficult. Well, takes some amount of time because, each object has non-trivial representation, and just comparing objects takes time as well. Okay, so kind of this is more of a, I guess methodology slide. So first of all, kind of, how are we gonna try to speed up these kind of problems? So first of all, how do we represent images? Kind of focus, narrowing down on the images case. So how are we representing them? Well, usually we represent them as some high-dimensional vectors. So kind of a most naive way to represent images is, let's say, take a binary vector where each coordinate corresponds to a pixel of an image, and then comparing two images is just computing Hamming distance between these two vectors. So if images are large, these are already kind of high-dimensional vectors, and even kind of computing the distance between these two vectors takes some time proportional to the dimension, and kind of a natural idea to speed up this task of finding similar pairs, and this is something that is still used in practice a lot, is basically to do certain kind of dimension reduction on these vectors. And let's say for Hamming vectors, kind of the most naive dimension reduction is just subsample a bunch of coordinates, compute the distance, the Hamming distance on the subsample coordinates. So note that we subsampled exactly the same coordinates, and this gives some estimate of the distance. Okay, so kind of more principially, this is an example of dimension reduction, and what really kind of what are the properties of this tool kind of a dimension reduction is that. It is a form of compression of the object. So it is a compressed representation of the object. So we don't remember everything about the object. We cannot uncompress it. So it is lossy, and but it is good for a specific task. So kind of as a tool for compression, kind of think about this as functional compression. It is good for the specific task, and the specific task here is computing the distance. Okay. So this is kind of one of these tools, kind of as a foreshadow of this general kind of sketching ideas. All right, I should mention here that nowadays this is not really the representation of images that one uses. Today you pass them through these black trapezoids, right, and you get vectors. Okay, suppose to say what was the joke is, okay, you really kind of pass them through neural networks that you train on some training data, but at the end of the day, kind of if you look at the neural networks, kind of at the end of the day, you still have to do classification. So if you look at the kind of penultimate level, then each image gives you gives a high-dimensional vector, and you really need to do basically what is maximum inner product to find the final class of the image or of the object. Okay, so this is kind of like dimension reduction is one tool, but more generally, kind of this is the pitch or methodology of kind of this talk, is that more generally what we can think about, or like what needs to be what we can utilize, are succinct data representations, of which dimension reduction is just one example. And we somehow want to use these succinct data representations, perhaps that have some properties of this sort, to design more efficient algorithms. Okay, and this is we'll see some examples today. I'm sure that some of these examples you've seen them, but just I want to put them in a bigger context. And I want to mention that at least in kind of theoretical computer science community, there has been a lot of other ways to do this succinct data representation. So sketching in particular is kind of a natural computational generalization of a dimension reduction, and generally was originally proposed in the streaming community. And there are others kind of more specialized sampling or metric embeddings and other methods. So I'm mostly kind of focused on sketching, but we should think about this as there are more ways to get these succinct data representations. Okay, so I'll here is the plan. Now this is way too much kind of to talk about, so there is no chance I actually can cover everything and give like a fair overview. So to give a disclaimer, this is really a random selection of a few topics that I thought would be cool to mention and would be relevant for the audience. And here are the three things that I'll mention. So one is numerical linear algebra. So hopefully more of you have seen work done here, the use of sketching here to speed up these algorithms. I also talk about similarity search, and I started with this problem. I should say something about it. And also the talk right after will be very relevant. We will set up the ground for the talk after. And then I'll spend a little bit more time here, where I'll show how to use somewhat different sketching for speeding up a particular linear program. Okay, so I think this is something relevant, but I expect that many of you have not seen it actually. Okay, so we'll start with one, and hopefully many of you have seen this. So this is more of a recap. So the problem that we will consider here is least square regression. So this is we want to find let's say XR which minimizes this L2 norm. So this is where A is a matrix where of size n by d. We'll usually think of n as being much larger than d. So d is dimension of vector x, and n is the number of samples, and we usually think of n being much larger than d. And we will allow approximation 1 plus epsilon. And this is really what Andoni talked about 2 days ago, right? So except that he considered the LP version. Okay, so I'll start from the basic. We'll start from L2 norm, and the idea here is it's termed sketch and solve. Actually, I was asking Ken the other day where the term comes from. I'm not exactly sure, but. We'll get back to the name a little later. But the idea is the following. So what we can do is, rather than solving the original problem, we just reduce the dimension of the problem. And in particular, we reduce the larger dimension, namely the n dimension. So what we do is we pre-multiply both A and B by a matrix S, where S is, you can think about S as a dimension-reducing matrix. Okay, so something of a sort of Johnson-Strauss. And we think about reducing dimension M to be much, much smaller than n. Ideally, perhaps not even depending on n, more like proportional to d or maybe less. Okay, so this is the idea. And so we solve this. We don't get precisely x star, but the hope is that the x prime solution is sufficiently good. Maybe we lose a factor of 1 plus epsilon in the objective value. Okay, so how to do this? And really this idea, I mean, this has been used in many papers. There should be 3 dots. So I think the first time it was proposed in a paper by Tamás Szarlos. A lot more has been shown, particularly in the paper by Ken Clarkson in the audience, and David Woodruff, also hopefully here in the audience. But there are many, many more papers that were working in on similar problems and using similar tools to improve the algorithms. But okay, let me tell you exactly what what they are doing. So, so what exactly is this dimension-reducing matrix? So we really kind of the tool. We think about this as a generalization, certain way to generalize dimension reduction. So it is called oblivious subspace embedding, and it is a map S, which again goes from dimension n to dimension m. Such that for, I assume that all of you have seen dimension reduction, kind of classical Johnson-Strauss lemma, which says that if you take random Gaussian matrix and then it is dimension reducing and it preserves L2 norm up to some approximation. Okay, so here this is a generalization in the sense of it doesn't hold for any particular vector, or let's say with high probability, but it holds actually for an entire subspace. Okay, a linear subspace, let's say of dimension d, and it preserves, so in a sense with high probability, it preserves the L2 norm of any point p up to 1 plus epsilon factor for any point p in the subspace. Okay, so it is something that holds for the entire subspace. Okay, and I should mention that there are different ways to use to take this matrix as kind of the latest kind of the I guess the ones using this oblivious subspace embedding. You can essentially use it kind of the way that I showed in the previous slide, where you just pre-multiply it and then solve the much reduced system. This will give you eventually a runtime which is order of number of non-zeros in the matrix A plus a term which depends primarily on dimension d, and it is a polynomial dependence on d and epsilon. There's various papers that reduced, yes.
So m depends only on d and epsilon, right?
Sorry?
M,
yes. M will be d squared by epsilon. So there are a few papers that improved what is the exact dependence of m on d and epsilon, but think about this as polynomial in d by epsilon.
With Michael Cohen's results being about among the best, right? If not the,
so
the best, actually.
What is the
embedding dimension?
What is the embedding dimension? I should perhaps.
Well, just what that m, how small that m could be. I think Michael has the best results along this one.
Yes. So yeah. So I guess it's proper to mention that Michael Cohen had the best bound on m in terms of as a function of d and epsilon. What is the exact bound, or is it? It is. So and kind of one way to get S, and this is from the paper by Ken Clarkson and David Woodruff, it's a combination of taking random plus minus ones. Think about this as a form of kind of random Gaussian vector, and combined together with the idea of count sketch, which is really, it was done in a different context in the kind of streaming community. And it's a sketching algorithm. It's like for those of you who have heard about it, but just I guess the point that I'm trying to make here is that this map S is really kind of based on the ideas that came out of kind of streaming community, of sketching community. Okay. So this is what you can get from this S. The idea of constructing S kind of is that multiplying by the linear map S should be done fast. This is why there is a lot of work in designing this map S so that it is efficient. Okay. So it turns out that you can, if you're unhappy with polynomial dependence in 1 over epsilon, it turns out that you can combine these ideas of oblivious subspace embeddings together with preconditioning, and this will give you time of this sort, where you'll have a factor of log of 1 over epsilon. Okay, so this is kind of this is roughly kind of how things go in for least square regression. So basically for L2 norm, but what if we want to do L1 regression? Okay. There is a question? Sorry.
Preconditioner was for what? I mean,
so you can compute preconditioner for A using oblivious subspace embedding.
so then it's not oblivious anymore.
Sorry? No, so you compute the preconditioner kind of. So the algorithm doesn't really work exactly in the way that I mentioned. So you compute precondition and then use different algorithm. So you just use the oblivious subspace embedding to compute the preconditioner. Okay. After that. Okay, so how shall we do the L1 regression? So in a sense, what we are basing here, kind of for L2 case, what we're basing on is that we can do this oblivious dimension reduction, kind of, so more fancier versions of Johnson-Lillichau's lemma. So in L1, there is no good dimension reduction in L1, so we don't even hope to do an entire subspace embedding. Okay, so this is a problem. Nonetheless, kind of, again, this was coming from the streaming or sketching community. There was a result by Piotr Indig who showed that, okay, there might be not a dimension reduction in the classical sense of dimension reduction, but there is a different object. There is a different way to kind of compress the object so that we can still recover the L1 norm of that object. So this is the sketch, and kind of you can think about this as a relatively generic definition of what a sketch is. So it is a linear map. Again, it reduces dimension from n to m. Now there is also an estimator. E is just a generic algorithm. I mean, I guess it's a specific algorithm in this case, such that for any, let's say, for any point P in d-dimensional space, we have that the L1 norm is approximated by an estimation, the estimator algorithm run on the sketch of a point P. Okay, so originally, kind of, what is the difference is that originally we really cared that this estimator is just computing the L2 norm, kind of. Okay, so here we're just allowing kind of an arbitrary algorithm. Okay, and kind of the rest is, is exactly kind of as you expect in dimension reduction kind of statement where you have a 1 plus epsilon distortion with some probability. Right?
Now the for all p has come out of the probability. So
yes, so
it's only for each single p, but
so this is for any p of dimension n here.
no, but that's not inside. For all is
this
not
is not inside. So that's what I mean. That's what I was saying, kind of that. Even before doing oblivious subspace embedding, we would need, a result even for dimension 1, kind of. So dimension 1, this means that you want to preserve the L2 norm of 1 point. This is what Johnson-Lillichau would give you. So what I'm saying for L1, there isn't an equivalent statement as Johnson-Lillichau's, even for dimension d equals 1. So what this statement, what this sketch is the equivalent of Johnson-Lillichau's. Think about this, as opposed to this is not really equivalent of oblivious subspace embedding. And I should mention kind of what this map as looks like. So it's a linear map. So you can just take a matrix which has random Cauchy random variables. Okay. And so you can use, ideas based on this to get certain improved algorithm for L1 regression. There is actually a slightly different way to do it and give slightly better algorithms. And think about this as a form of let's call it a poor dimension reduction. Okay, maybe we don't get a very good dimension reduction, but we get a poor dimension reduction. Which basically is, looks more like the oblivious subspace embedding now, except that instead of getting a 1 plus epsilon approximation, we're getting a much larger approximation, which is polynomial in D. Okay, but over, so I guess this is the poor oblivious subspace embedding result. Okay, and how the map S will look like, so it is. It is a map which combines ideas of multiplying by 1 over exponential random variables and the count sketch that I mentioned from the previous slide that was used for L2. Even though you get this approximation kind of much larger approximation for doing one oblivious subspace embedding, it turns out that you can use an iterative method to reduce the final approximation to 1 plus epsilon. And what you can get at the end of the day is an algorithm that runs in time, which is number of non-zeros, times log n, plus something polynomial in d by epsilon. Okay, and I should mention that 2 days ago, Intat talked about joint work with Michael Cohen and other authors. I don't remember. Yes, it's an unpublished paper. Sorry, and with?
But if we talk about poly epsilon dependence, then probably the current fastest L for me is the paper by Michael with Japan.
Michael?
With Japan.
Richard Peng.
Oh, Richard Peng, okay. Which runs, it is still of this form.
I don't remember the running time, but they basically reduce to a d by d problem. And then you use whatever problem to solve the d by d problem.
Right. So this is, I mean, but it still be a polynomial in d by epsilon, right?
Yeah, but you get the optimal O1 there.
Oh, I see, without the log n.
I mean the optimal on the O1. I don't remember they get log n or maybe something log or I don't remember.
Okay, so it is, right, so I mean this is, there are a number of papers that achieve it. Like I'm mentioning your result that at least for LP, where P is strictly bigger than 1, you can actually get a logarithmic in 1 over epsilon dependence. Right, but this is unpublished paper, ask Intat about it. So this is kind of, the general overview of kind of, how things roughly work for numerical linear algebra and how we can use sketching ideas for speeding up algorithms. And I should mention that, very much more. This is, I just want to kind of give you some kind of highlights or, rough sketch of how things would go around. I definitely recommend taking a look at David Woodruff's survey in FNTTCS. Well, I guess there are also a number of papers since then that appeared. But you can apply these kind of ideas to many more problems for long-rank approximation and as well as optimization. And I think Mandolin will talk about low-rank optimization problems, which will use sketching ideas later today, as well as matrix implication and numbers. Okay, so this is, so I went a little bit quick through that, hopefully because many of you have seen ideas from there. So let me go further and kind of cover some other things that probably many of you have seen less of. So first, similarity search. So this is related to the problem of approximate near neighbor, where this is kind of related to the original problem that I mentioned. So here we need to preprocess endpoints. We are given also an approximation C. Think about C as 1 plus epsilon, but usually, okay, we don't think of epsilon as being too small. Think of approximation as being 2, let's say. And the problem is that preprocess this data set so that given a query point Q, we report the closest point P star, or maybe closest up to some approximation factor C. Okay, so this is the nearest neighbor. We'll actually look at a related problem of near neighbor, which is formally connected to the nearest neighbor, but it's just easier to talk about near neighbor problem, where we have a threshold R. So instead of just reporting the closest point up to some approximation, it is OK to report any point within distance R from the query point. Okay, and what it means to be approximate here, the formal definition of approximate near neighbor is that as long as there is some point in this green ball, it is OK to report something out either from the green ball or from this, I guess, no man's land in the gray area. Okay, but it is not OK to report something from the red area. Okay, so this is the formal definition of approximation, and the main parameters that we care about here is basically the space to store this data structure, plus the query time, how much time does it take to answer this query. Hopefully it will take time which is sublinear in the number of points. Okay, and basically solving this data structure is, basically related to the best way to solve the original problem that I mentioned in my first slide, namely finding similar pairs of points in a data set of objects. Okay, so here kind of the, again, focusing on, like what are the data representation primitives or the succinct data representation primitive. So here kind of the tool or the idea was proposed by Nick Matwani back in 1998, and it is termed locality-sensitive hashing. How many of you have seen the definition of this? Oh, okay, about half, a little more. So this is, I'll define it. I mean, this will be related to Moses' talk later today. But I mean, what is it? What it is? It is really a random hash function defined on a high-dimensional space of dimension d. And a random hash function in dimension d, it can also be thought of as a random space partition. Okay, so it is a random space partition because you can think about each part as being the locus of the points that have exactly the same hash code under this hash function. Okay, and generally what we want is a partition where a closed pair, so a closed pair is, this is an example of closed pair. Formally, it is a pair which is within distance r with our threshold, kind of similarity threshold. We want the probability that we are in the same bucket, namely the hash codes are equal, is to be high, as opposed to the far pair of points, namely q and let's say this p prime, which are distance more than cr. We want the probability that they collide, have the same hash code, to be small. Okay, and then to solve our problem, we can just build a hash table. This will be the entire solution for this problem. In particular, for this, let's say, 3-point data set, you just store all the buckets and the points in those buckets. And then given a query point q, you just look up the bucket. Let's say this is the bucket. And now given these two conditions, this means that the points in this bucket will be exactly the points that we want to report, namely the points which are within distance r and none of the points which are far. Okay, now this sounds too good to be true. In particular, you can see that there are boundaries. It is easy to put points on two sides of a boundary which are very close, yet they are separated. So it is not really possible to obtain this probability to be high for any reasonable threshold r. Okay, so we settle for something less ambitious. You say, well, as long as there is some gap between these two probabilities, so if this is small, maybe this is not so small, then we still are in game. We can still do something not trivial. So this means that maybe one hash table will not succeed, but maybe you can use a number of hash tables. Okay, so pictorially this means that you'll just sample a bunch of these random space partitions, build a hash table for each of them, and then for every query, you just look through all the tables. Okay, and kind of what is the, I mean, of course, the main object here, kind of, the main mathematical tool here is this random hash function, basically this random space partition, and the quality of our data structure will depend on the quality of this random hash function. In particular, what it will depend on is how does this profile of the function looks like. So we can draw this function, which is the probability of collision of 2 points, as a function of the distance between these points. And in particular, these 2 probabilities are 2 points on this curve. We want them kind of the gap between these probabilities to be as large as possible. And how do we exactly measure the gap? I mean, if you go through calculations and see how many hash tables do we need to take, which basically controls both the space and the query time, you'll figure out that it will be the number of hash tables will be n to some power rho, where think rho is some kind of capacity or quality of this hash function, and it will be a function of its probabilities p1 and p2. I mean, it's slightly uglier function, but this is the right function. It's not too hard to prove it. And let me just give you kind of 2 examples of LSH maps. So the first one is from Datar, Indik, Imurlika, and Mirokny. And basically, if this is the space, the idea is to just impose a randomly shifted and rotated grid. Okay, so pictorially, this is, let's say, your data set. You take a grid, you randomly shift it, rotate it, and basically this will be your partition, right? So these are different buckets all these points have the same code, let's say. Okay, and you can get, compute what you get as the exponent, this function rho. You'll get something like 1 over c, where c is the approximation. And I'll just run an example of c equals 2. So for approximation 2, you get the exponent, which is a half. So this means the query time is roughly root n. Turns out that you can do better. You can get an improvement from a half to a quarter. And the idea is that rather than partitioning the space into grids, basically into this into cubic cells, it's better to partition the space into balls, basically. So we cannot really partition even two-dimensional space perfectly into balls. So you do something like this. So picture is worth 1,000 words. This is how you partition, where kind of these grids of balls are randomly shifted. Okay, so this is kind of the idea introduced in a paper we had of Piotr Indyk a while ago. Okay, so this will be a random partition. Kind of each colored connected part is basically a bucket. Okay, so can we do even better LSH maps than this random partition into balls? It turns out that no, and the real reason is that it's an example of isoperimetry. You can improve lower bounds, and the lower bounds basically showed that this is the optimal way to partition space, and this is due to Motwani, our Panigrahi, and later due to O'Donnell, Wu, and Zhu, who got the tightest bound. Okay, so I just wanted to show this example. I should mention, can't talk about LSH without mentioning that in more recent work, we actually showed that you can get better maps. So you can basically break through this lower bound if you allow your random space partitions to depend a little bit on the data set. Okay, ask me about the talk if you're curious about this. It's not really important for this discussion, but just to state that you can get actually better ROS if you are interested in this problem. But I mean, so as defined LSH, I define it as a tool to solve nearest neighbor search. But it turns out that you can use it for much more than purely nearest neighbor search. So in particular, the applications of this idea, or most natural kind of outside this problem, is to the maximum or minimum inner product. So where you have a bunch of vectors and you have a new vector, you want to find the vector which maximizes or minimizes the inner product of my query vector. Sometimes it comes up as by the name of MIPS problem. And this particular problem is used a lot in speeding up certain optimization algorithms. For example, gradient coordinate descent, kernel function approximation in some work due to Ben and Ali Rahimi a while ago, as well as, and this is relevant for talk later today, to kernel estimation. So later today, Moses Cherikar will talk about how to use locality-sensitive hashing for faster kernel estimation problem. Okay, so he'll define the problem and talk about it. And I guess in the last 7 minutes or so, I'm the keeper of time, right? It's also, that's the advantage of self-introduction. So let me talk about the last part, which is about geometric mean cost matching. Okay, so and kind of going back on kind of more like a philosophical level. So far, kind of the way we exploited the sketches or kind of these tools for succinct data presentation is to really compress the input. All right, so in some sense there was, okay, this is like very hand drawing kind of picture. In some sense we have certain computation to be done, let's say for a least square regression. And what we did was say like, well, maybe we can pre-multiply our matrix A and B by certain dimension reducing matrix. This reduces the size of the input, and once we have smaller matrices, it is easier to run standard exact algorithms, for example, to get much faster computation. But what I'm trying really to advocate in general is that we can really think about succinct data representations also to compress not just kind of the input, but really kind of the internal state or partial computations that we have done, we might be doing in a problem. So using internal sketches to to compress internal state or partial computations. Sorry.
This is better.
Yes. So, and this is the last, I mean, this last bullet point is really about that, okay? And let me basically quickly tell you about this. So the problem is the following. So it is bichromatic mean cost matching. So given two sets A and B of size, let's say n, in some d-dimensional Q-linear space, we need to find mean cost matching. So this is an example. This problem appears under many names. In image vision, it will appear by the name of Earth-mover distance. In math, it usually is called or OR, it's called optimal transportation problem or Wasserstein metric and so forth. Okay, Wasserstein metric of type 1. All right, and classically, how would you solve this problem? So, classically, you can set up an LP to solve this problem. It will have n squared variables. So this is kind of, an LP, one way to set up this LP. So you'll have pi ij, which says whether we match point, or how much of a point pi from the red set we match to the point j from the blue set. Okay, this is the color coding. Set A is red and set B is blue. Okay, and so this, if you set up LP this way, right? It's like, never mind. If you manage to solve, so you set up this LP with n squared variables. So the best you can hope for is linear time in n squared, roughly, right? So actually, there is an upcoming paper by Alskurler, Weed, and Rigolet, upcoming in NIP 17, who basically showed that you can solve this LP for arbitrary cost function in time which is roughly n squared by some function of epsilon, polynomial in 1 over epsilon. So this is kind of near linear time. Okay, this is as fast as we can solve this, we can hope to solve this LP.
Find an integral solution to LP, or they solve the LP approximately. What
Sorry?
is epsilon? Is it the objective? Find an integral solution that is.
We can discuss. So not quite, but I mean almost, but not quite. It's not multiplicative 1 plus epsilon. So there is a little bit more factors. This is why there is a star here, but
Find an integral solution.
Sorry?
Do they find an integral solution?
Oh, I don't know. Is Jason in the audience?
No, there might not be. So it's no.
I guess no. But yeah, I mean there are more caveats here, but I mean we better talk about them after the talk. But really, kind of, here we can, oftentimes kind of the most classical way to use this problem when it appears in image vision is when d is equal to 2. Okay. So these are points in two-dimensional space. This is kind of one of the most classical applications. And here we're saying, like, well, our input is really order of n. It's not order of n squared. We can compute all these distances. So we really should hope for something which is whose runtime is much less than n squared. Okay, so maybe a proportional to linear in n. And this is what I wanted to mention. Basically, a technique that we introduced with Sasha Nikolov, who is in the audience, Krzysztof Onek and Grisha Yaroslavtsev, actually a few years ago, where we showed that we can solve this problem, and in general the transportation optimal transport problem, in time which is near linear, well, n to 1 plus small of 1, for fixed dimension d and fixed approximation epsilon. Okay, so dependence on epsilon is actually worse than one polynomial in 1 over epsilon, but for fixed ones you can get this amount of time. And well, we called our framework solve and sketch. This is different from the first thing that I mentioned, which was called sketch and solve. And I know it's a nice joke, but it was really independent names as far as I know. Right? It's anyways, so this is what I wanted to mention, kind of this, basically this algorithm. Okay, so how do we do it? And really, you should think about this as some very fancy divide and conquer algorithm. Okay, to solve this problem, the mean cost matching. Okay, and this is how it works. So first of all, you have to do divide. So somehow we'll take the problem, we partition it to a tree, basically, not to deep tree. And we'll try to solve the problems recursively and then recombine them until kind of at the top we'll have a solution. Okay, so this partitioning will be, related to kind of relatively classic kind of geometric partitions of a space. But what we want to do is we want to take the space and partition it somehow hierarchically in a nice way. Okay, so let me use this kind of intuitively at the moment, non-formally, but think about kind of LSH type partitions would be good. And this is kind of one way to partition the points. I just draw, a number of points, not everywhere. But you can think about this like red partition as like kind of first level partition, and then these smaller blue partitions are kind of second level partitions. Okay, so this is part one. Now, what do we do in each part? So in each part, what we try to do is the following. We try to compute, so let's say in this part, so you can think about, each of these parts will correspond to each of the smaller parts will correspond to each of these leaves in this computation tree, in this divide and conquer. So this is kind of one way to see it. Okay, so what we'll try to do is compute the local solution in each of these parts. Okay, so maybe this is the local solution in each of the parts, right? So this is kind of partial matching as much as we can. Then what we do is we sketch the solutions. So we cannot really, recombining this kind of at the top, is as hard as solving the entire problem. So what we're trying to do is actually just compress what has happened here into something, I guess some kind of stars. This will be some sketches. And then at this node, this computational node, will just be recombining the sketches that we obtained here to form a more global solution, kind of a more global matching. Kind of this will correspond to matchings across the parts in the first level. Okay, and I guess, and then you sketch whatever you obtain, some weirder object, and then you send it up in the computation tree. Okay, and of course, what exactly needs to be solved here, like what are the main, things that we need to discuss? How do we partition the space in hierarchically? How do we compute this solution for the local view so that we can recombine it later into a global solution? How to sketch such solution and so forth, right? These are kind of the main things to be done. And so, applying this particular framework for our geometric matching problem. So this, partition of a space, any reasonable partition will work. Let's say randomly shifted quad trees, relatively classic idea for this kind of problems, will work. But the first thing where we run into a problem is computing a local solution for the problem. So just to give you kind of an intuition of what's happening, so this is grid. These red grids is the partition of a problem. Okay, so each cell kind of is a different part. So now at the first level, we need to solve the problem given the local view. So this means that we see a bunch of red points, some blue points. There might be points outside. We don't know about them. We just need to solve these kind of sub-problems. And the problem is that you cannot really compute a local solution so that you can patch it with the rest of the problem later into a good global solution. And this is the reason. So suppose you take, you see these points. So you're saying like, well, given these points that I see them, the best way to match them is, well, pretty much this. If there is nothing else, this is the best matching. But then, somehow, at the next level, we uncover everything else, and we need to recombine this with the rest of the points. And it turns out that we should have taken exactly the opposite alternation. So, and once we have committed to this kind of matchings, there is no way, this should be the right way to do the min-cost matching. And once we have committed to the wrong alternation, kind of to the wrong matching, there is no way to patch it up later to get good approximation. Right? So once we have committed to this matching, there is no way to fix it to get an approximation which is close to 1 plus epsilon, right? To get an approximation less than 2. So really what we need to do here is not to compute just one solution here for the local view. What we really need to do is to compute all potential solutions that are valid solutions given what will happen later in the other parts. Okay, so let me just define exactly what it means. So sketching all solutions, this is roughly how it will look like. So so you'll define something which are called portal points. So in a sense, think about this as, you can think about the matching as a flow kind of problem. And you're saying that, well, when we're matching, let's say, points and cross these boundaries, we really should route them through these portal points, these big axes. So we're saying that once we kind of have this cell and we want to match something from this cell to something outside the cell, you're not allowed to go directly. You have to go through this portal. So there is kind of entry and exit points into the cell. Okay, and the advantage of doing this is that we can define a very small, something that will depend on epsilon only, number of such portal points. Okay, and now we can define the following solution function. So solution function is a function which maps from something of dimension k into positives. And basically, for any input x of dimension k, we define f of x to be the following. So assume that there is, we specify what is the amount of flow in and out for each of the portals. And you're saying, assuming that this is the amount of flow that goes in or outside of each of the portal, what is the best solution of the matching with the points that are inside this part? So you can think about this x as defining the interface, and you're saying the solution function is a function from the interface to the optimal solution. And now the idea is to sketch this function f, and it turns out that you can sketch this entire function f. Okay, and the size will be something like logarithmic log n by epsilon to power k. So in particular, it will get an exponential in one over epsilon dependence. So not particularly good, but I don't know if this is optimal or not. I mean, perhaps one can do better. But given such sketch, you can estimate this function up to 1 plus epsilon approximation. Okay. So
The question.
yes.
How is this connected to the idea of a core set?
It is a form of core set. I mean, I see core sets as a type of sketch. So I guess for me, the question is moot. But it is, you can think about this as a core set. But the sketch is really, core sets are usually you take a subset of your data set, kind of. If you, it's not a subset of a, okay, it's evaluation of f on certain points, on some geometric discretization of your input space. This is what really.
Property that it's good for.
Yes. Precisely. You can take that and you can patch it with things that are outside, and it is precisely. Okay. So in the overall algorithm, we kind of, at the next level, we need to recompose these sketches into kind of a sketch of a solution kind of in the combined region. And it turns out that you can formulate this as some linear program, actually. So at each of these nodes, at the end of the day, it will be solving a small linear program. And so just to reinterpret this, what happens is that you take this LP that corresponds to bichromatic matching, you decompose it into kind of in this hierarchical fashion into many smaller pieces. So each of these triangles will be an LP of small size. So really, you can just solve those LPs with any polynomial time solver, and you'll get the stated time, which will be basically nearly the number of points. Okay, and okay, this is it. So I'll finish here. I guess the main point that I wanted to mention is that we can think about succinct data representations as certain kind of objects the definition is kind of problem specific. For different problems, you might have different properties. There are different ways to get these succinct data representations. So I mostly mentioned dimension reduction and sketching, but there are other ways as well, kind of based on, let's say, metric embeddings or sampling, and to use these succinct data representations to get efficient algorithms. And I gave you, 3 examples, but this is just a very small selection of the ways that we can use these succinct data representations to speed up algorithms. And I'll end here. Thank you. Questions? Okay. If not, then I guess we reconvene at 10:45 for the next talk.